Welcome to JCON!
Hi everyone, my name is Richard. I'm one of the organizers of JCON, and on behalf of the whole JCON team and our sponsors, I would like to thank you for joining JCON today. We appreciate your attendance and hope you will have fun and learn something new. We got an exciting agenda for you to explore. Our content board had to choose from 280 submitted session proposals. So thank you to the content board and all and everyone who submitted a proposal. With over 130 speakers from 56 countries, 160 sessions, 10 workshops, and 2,500 attendees from 6 continents and 77 countries, this is the greatest JCON yet. A big thank you to everyone who made JCON happen and our partner Java user groups. A special thanks to our sponsors. Make sure to check out their websites, products, and services for the Java community. To kick off our first keynote at JCON this year, I would like to welcome the one with the awesome Twitter handle I'll always be jealous about, @SpeakJava, Deputy CTO at Auswahl Systems, Simon Ritter, and co-organizer of JCON, editor-in-chief of JAVAPRO, CEO of MicroStream, Marcus Kett. Welcome, guys.
Thank you. Thank you very much, Richard. Thank you for your introduction, and thank you for joining JCON. Hello, everybody. Welcome. Yeah, it's great to be back, and today with a keynote together with Simon Ritter from Azul. Fantastic to have you on board, Simon. Thank you for that.
Thank you.
This talk is all about in-memory data processing with Java. And it's because we with our customers and partners and yeah, together with lots of developers at all Java developer conferences, talking about all the time about performance. And it's because the systems of the future, they will produce tons of data. And we saw this in our intro video. And the systems of the future must be able to consume tons of data. And it's all about AI, machine learning, and the fastest systems, they will win, and the slow systems, they will lose in the future. And at the same time, we know that database systems are often too slow, and database development is often too complex, too effortful, time-consuming, and expensive. Yeah, there are more and more NoSQL approaches coming up, and so the question is: are the database systems of today, and are the modern NoSQL database systems, are they really fast enough? And people talking about, is Java really fast enough to meet all these requirements of for these applications of the future? And currently, we're already working on quantum computers, right? And the question here is, should we really wait until we have quantum computers, or can we improve software systems? And I like to talk about this is not a new approach. It's actually it's an old approach, but it's not too popular. But it is a very interesting approach, and it's all about Java in-memory computing. And this concept is called system prevalence. And we believe that the Java is already fast enough and is really super fast technology to process all the data in memory with pure Java. Nothing else. No using alien database systems that work totally different from Java, from the object-oriented approach of Java. And to do that, we already have the best performance. So with the JVM and its JIT compiler, its amazing JIT compiler, we believe Java is already fast enough. And we also have the perfect data structure. We have objects, and we can build elegant object models, and so we can do really everything. So everything is free in Java, and so we can use single objects. We can use also lists, collections. Any Java type can be used in a Java object model, and we only need Java classes for that. So we don't have to use completely different data structure in Java, and we don't have to convert data behind the scenes, generate code or something like that. And we also have a very powerful query language. With Java's Streams API, we are able to search object graphs and really huge object graphs in microseconds. We can use parallel streams and accelerate our queries. And so we have the perfect programming language. We have the perfect data model. It's actually a multi-model data structure. So all these database vendors out there, they are working on multi-model data structures. We have multi-model data structure from the beginning. We have the perfect query language. The queries are executed super fast in memory. And we have additional libraries like GraphQL, Lucene, and we have JVMs that are able to manage huge memory sizes already, like Azul. So in Java, we already have everything for building ultra-fast in-memory database apps and microservices. But what's about persistence? And system prevalence is actually the simplest way to get persistence for your POJOs. And system prevalence is a simple software architecture pattern that combines system images, which means snapshots, with transaction journaling to provide speed, performance, scalability, transparent persistence, and transparent live mirroring of computer system state. And this is a very interesting concept because it's so simple. And Martin Fowler, almost 10 years ago, wrote a blog article about such a system, and he was very excited about the performance. And the question here is, why is this not that popular in practice? Obviously, there must be a problem. And there are some challenges, of course, because the snapshots, they are mostly too big, and snapshots are too time consuming. It can take too long to restore snapshots after a system restart. And this is not really suited for microservices. And you also can lose data between snapshots. So this is also a huge risk. And then you're limited in terms of the memory size. So your database can't be bigger than your memory size. In addition to that, you will produce lots of traffic by using snapshots and snapshotting the entire database. So this might be the reason why system prevalence is not that popular in practice. Additionally, we use Java serialization for persisting our objects, and Java serialization is slow and has security issues. Altogether, there are lots of challenges, and I think this, personally, I think this is the reason why this concept is not as popular as it should be. And lots of developers, they have concerns about the memory size. Is it really possible to write algorithms that are as fast as databases can be? Or is a database faster in any case? So this is the big question. Simon, maybe you can tell us more about the performance of a JVM. Is this really possible, or is this only my personal dream?
Yes, thank you very much. It's an interesting question, isn't it, when we talk about performance? Because certainly if you go back in the history of Java right to the very beginning, Java was criticized as being slow compared to natively compiled languages like C and C++. And so what's changed between then and now? Well, a lot. Obviously, the Java virtual machine uses a number of different algorithms internally. It does things differently. But we're still left with a number of distinct performance challenges when it comes to JVMs. Even though they scale up to the sort of internet scale of applications where we're dealing with very huge data sets, as Marcus was talking about, what is it we actually need to look at? The first of those is around latency, the impact on how quickly we can respond to a request because of something that happens within the JVM. And if we look at what results in latency, the biggest contributor to that is garbage collection, because most algorithms that we use when we do garbage collection are what are called stop the world. So they have to pause the application threads in order to be able to do the work that they need to do safely. So when they're marking which objects are still in use, we need to pause the application threads and do a marking phase. When we're relocating objects within the heap, we need to pause that so we're not getting inconsistent data and changing things in the wrong place. So that's what we find, is that latency is primarily down to garbage collection. There are a few other things, but garbage collection is the big one. And the pauses that we get, and this is the big thing here, you see, when we're talking about big data, the pauses that we get with garbage collection algorithms are typically proportional to the heap size, not the live data. So you may have a very large heap, may not have that much data in there, but you end up with a long pause when you need to do garbage collection. The second thing that we need to look at is throughput and how quickly we can process things when we need to do that. And that is down to this idea of JIT compilation, just-in-time compilation. That happens adaptively, meaning that when we start off, we're running bytecodes, we're interpreting those bytecodes to convert them from the virtual machine instruction set to the platform instructions that we need to run on that particular processor. As methods get used more frequently, we'll notice that within the JVM, we'll then compile them using the C1 compiler, which is a very fast compiler, but doesn't optimize heavily. Then once those methods get used more and more, they get recompiled using the C2 compiler, which uses profiling information we've collected, generates much more heavily optimized code. That's really good because it actually enables us to get better performance than you would get with statically compiled, ahead of time compiled code. One of the key things that we can do there is speculative optimizations. But even though that's good, there's a bit of a downside to that, because also you have what are called de-optimizations. You've made an assumption about how the code is working, you compiled based on that, and then it turns out to be false, so you have to throw away the code and recompile it. So the level of optimization that we get there is really key to the performance we get of the JVM overall. And then the last thing that we need to consider in terms of performance is warm-up time. Because we go through this adaptive compilation, interpreted mode, C1 compiled, C2 compiled, that takes time. Identifying the hot methods, compiling them, making sure we've got all the profiling information and so on. And the real drawback to that is that when we start the application again, we go through the whole same process. So we just start from scratch and we do everything again. So what we've done at Azul is to think about how can we improve the JVM? What can we do to make it better? And what we've come up with is what we call Azul Platform Prime. It used to be called Zing. Now, rather than starting completely from scratch, we took OpenJDK, the open source version of Java, and we said, yep, most of that's really good, but there are a few things that we could change to make it even better. Having done that, what we really want to make sure is it's a drop-in replacement for other JVMs. We don't want to introduce new libraries. We don't want to have people recoding. We don't want to have to even recompile their applications. So this is just about taking your same class files, your same jar files. All you need to do is change the position where you find your JVM from, your Java executable, and off you go. In terms of what we've done, we've replaced all of the collectors in Hotspot, the serial collector, parallel collector, CMS, G1, Shenandoah, ZGC, with one called C4. The second thing we've done more recently is looking at that JIT compilation side of things, and we've replaced the C2 JIT compiler, the heavily optimizing one, with one called Falcon. And then the last thing that we've done is to look at that warm-up time and introduce a thing called Ready Now, which is designed to eliminate that as much as possible. Now, one of the key things about Azul Platform Prime is that we only support it on Linux. Now, that's a technical decision, well, not a technical decision, it's a decision based on demand from the market. There's no real reason we couldn't put it on Windows as well. But what we find is most people who want to deploy these enterprise large applications are using Linux in their data center. The reason that we do that is because we also take advantage of the fact that we can introduce things into the kernel through our own kernel module or through some more modern system calls and be able to manage memory in a more efficient way for the JVM at the operating system level. The reason for that is that if you think about the JVM, it's a very specific user of memory, and the virtual memory system in Linux is designed for general purpose applications. So we do some things to make that even better. What this allows us to do is to scale up to these very large data sets that Marcus was talking about. So we can go up to a maximum heap size right now of 12 terabytes. That's in core memory, 12 terabytes. You need a pretty big machine for that, but we do have some customers who do that. So how does this work? Well, in terms of C4, what that stands for is the continuous concurrent compacting collector. Essentially, that tells you exactly what it does. It's a garbage collector. It runs continuously in the background to monitor what usage you got, how quickly you're allocating objects, and so on. The really important thing is it is a fully concurrent collector, meaning that all phases of collection are done concurrently with application threads. Even though we do that, it is a compacting collector, meaning that we will relocate objects within the heap to eliminate fragmentation and make the usage of memory contiguous, but still doing that concurrently. In terms of the basic approach we take, it is similar to other algorithms in that we use a generational heap space. We divide the heap into young generation and old generation. That makes sense because most Java applications, almost all Java applications, will allocate objects, and those objects will only be used for a very short space of time. If we can collect them in the young generation, then we avoid placing a load on the old generation, which contains our longer lived objects and the more sort of steady state set that we have for the application. So it makes a lot of sense to do that. In addition to being concurrent, all of the phases that we have will execute in parallel. We can apply a number of threads, use a number of cores, and have the work happen in parallel to minimize the amount of time it takes to do that. Very important part about this algorithm is it doesn't have a fallback situation, which many other algorithms do, where they will eventually say, too much fragmentation, we need to do a full compacting collection on the old generation. That's when you see those very long pauses that could be seconds, minutes, in some extreme cases, even hours. The way that it works is using a fairly straightforward algorithm. It's mark, relocate, and remap. And the way that we can do the work that we do concurrently with the application is through what we call the loaded value barrier. And that's essentially a read barrier that intercepts the references to objects every time you access an object. That allows us to enforce two rules, which means that if we're in the marking phase, identifying which objects are still in use, every object that you get a reference to will be marked. So there's no danger of accidentally garbage collecting an object that you're still using. Second thing that we can do is we can guarantee that in our relocating or remapping phases, the reference that you get to where that object is in the heap will be correct so that you can make changes. If we're moving it around, you won't lose your changes. Now, some people will say, well, hang on, doesn't that introduce an overhead in terms of performance? So you're degrading performance. And the answer is sort of yes and no. Yes, technically it is, because we intercept every reference to an object. But the reality is that because we only use two instructions, we're using bits in the object header, doing a test, determining if we need to do something, and if we do, jump to a handler, those two instructions in terms of the typical x86 architecture is a single micro operation, less than 1 nanosecond of overhead per reference. So compared to L2 cache, L3 cache, main memory access, it's way less than that's going to place on the system. How can I show you this works? Well, what we've done is create a small tool called JHiccup, and that basically measures the latency of the JVM itself and its impact that it would have on the application. So we're not measuring the latency of the application, how long it takes to respond to requests. This is the impact that the JVM itself has on the application. This is a simple demonstration here of a system running Elasticsearch. And we essentially took a system, we ran the same application with the same workload twice. First time we did it with Hotspot, second time we did it with Azure Prime. 128 gigabyte heap, so reasonable size, not huge, but a good size. And if we look at the left-hand graph, what you're looking at there is the latency. So high spikes are bad. And we can see that a very typical graph of garbage collection. We've got lots of small spikes, which are minor GC pauses, the young generation being collected. And then we've got two big spikes, which are major GC pauses, the old generation being collected. Same application running on the same machine. Right-hand side, we rerun the same thing with Prime. Now, you might look at that and say, well, hang on, you're saying that spikes are bad and big spikes are really bad. Compared to the left-hand side, that doesn't look very good. So what are you telling me in terms of this being better performing? But I've been deliberately misleading, and I've actually scaled the graphs differently. The left-hand graph is 0 to 8 seconds, meaning our minor GC pause is around half a second. Our major GC pauses are 5.5, 6.5 seconds. The Prime graph is scaled from 0 to 80 milliseconds. So if I set those graphs to use the same scale, we now see the reality. So this is always good to show customers. So you show the reality and suddenly all that garbage collection latency just disappears. There's a few very, very minor spikes, but remember this is measuring latency that's associated with the operating system and the hardware as well. The other thing, as I said, that we've done is to replace part of the JIT compiler. And again, we looked around to see whether there was work that we could leverage that other people had done in open source. And there was. There's a really good open source compiler project called LLVM. It's primarily designed as the code generation part, the back end of a static compiler. It's designed for languages like C and C++ or Go, various other languages. What we did was we took that work and we said we could integrate that with the JIT compilation system, make it work with the JVM. Once we'd done that, we contributed that work back to the project so that if other people wanted to use it as a JIT compiler, they could. What this allows us to do is to get better performance out of the code that's generated for the methods that are compiled. And that is really quite significant because certainly some of the things that we can do there are things like better intrinsics. We can do more inlining of methods. And one of the sort of big wins that we get at the moment is through better use of vector instructions, very wide registers, multiple data, single instruction, and being able to execute the same operation on a number of elements in an array in parallel. By being able to recognize situations where that can be used in a better number of places, we can get better performing code. And that's just one example of what we can do there. So we can make use of the fact that we get better performing code. And so the overall throughput of the applications running on top of Prime will be better because we're getting better instructions out of the compiler. Last thing to mention is this idea of ready now warm-up technology. What we do there is we say, okay, let your application run until it has warmed up and you're happy with the level of performance. All the methods that are needed are compiled and have been compiled with C2 or with Falcon, and then collect a profile. And that profile consists of all the classes that are currently loaded, all the classes that are currently initialized, the profiling data that was collected during the runs of the interpreted mode and C1 compiled code, and any speculative optimizations which failed. Because what we don't want to do is to make a mistake. So if we know which things we had to throw away and had to recompile, then we can avoid that in the future. What this allows us to do is to gather data over a much longer period of time. So we don't have to just do this straight away. We can wait 2 minutes, we can wait 2 hours, you can wait 2 weeks if you really want to, before you collect your profile. So you make sure that the application is running at the level that you want it to. Similarly, you can actually collect profiles for different workloads. You can have a Monday morning profile, a Friday afternoon profile. And then what we do when we restart the application, we use all this information. So we load all the classes we can, initialize all the classes we can, and compile all the methods that we know we're going to need before you get to the main entry point. That way, when the application starts running its workload, it's running at about 98% of the performance you had when the profile was collected. There's a few things we can't do in terms of getting that 100% straight away. There's various things around the way that the JVM is specified and what must be done in a sequence to start the thing up. And there's also a few issues around things like Lambda expressions that use invoke dynamic, and that makes life a little harder for us in terms of the way that we generate code. But essentially, by the time you've run 3 or 4 transactions through your code, you'll be at 100% of the performance you had before. The effect of that, again, using a latency graph, if we look at it before ready now, we see a sort of up and down graph as we're compiling, we're throwing away code because we're having to de-optimize, recompile. If we look at it with ready now, suddenly we flatline that graph. We don't have the problems of latency introduced by that compilation and so on. So it's much, much better, again, from performance perspective. So just to kind of round up this particular section, the idea behind Platform Prime is make your Java start faster through the idea of ready now, make it go faster by using the Prime Falcon JIT compiler, and then make it stay fast by eliminating the problems of GC latency. So that's what it's all about, as a simple replacement for other JVMs. No recoding necessary, just use that and get the best possible performance from your JVM. So with that, I'm going to hand back to Marcus. So I'll stop my share. Let Marcus share again. And you're on mute. Still on mute. No.
Thank you, Simon. That sounds awesome. And this fits perfectly together with MicroStream and our approach, or the approach that that we prefer in terms of database development. And this is the reason why now we announced that we work together and together we build systems for our customers and try to accelerate MicroStream applications by using a Azul JVM. And what we have done is we have improved our performance demo. So some people know this performance demo already, which runs on our website. But what is new, this runs with a Azul JVM. And here we can see 2 applications running. And one application is built with Hibernate and cache and uses an Oracle database. And the other application uses MicroStream. And here we can see all the queries are executed sometimes 10, sometimes 100 times. and sometimes more than 1,000 times faster than by using Hibernate JPA queries. And this is really incredible. And how does this work? Back to this slide, to this system prevalence approach and all these challenges I've mentioned already. With MicroStream now, we have eliminated all these issues completely eliminated. And now we have built a game changer with MicroStream. And now we have open sourced it completely. So we visited many Java user groups, and many people, they gave us hints, and so thanks for that. So we are really proud to be able to open source MicroStream now, and you can download it from our GitHub page. And how does MicroStream actually work, and what is the difference between the previous prevalence system approach and MicroStream? With MicroStream, we built a new serialization from scratch. So this is not based on the Java serialization. This is a completely new written serialization. And with MicroStream, now we are able to serialize the entire object graph, or only subgraphs. So you as a developer, you can decide if you want to store only some object references or the entire object graph. And mostly you will store only a subgraph. And also you can load and restore your object graph in the memory anytime, at any time. And we have added database connectors so that now we are able to persist the object graph or subgraphs into any database system. So the base of MicroStream is a serialization written from scratch. On top of that, we have built MicroStream implementation for the JVM and also for Android. And on top of that, we solved all these problems, like what happens if classes change. So we implemented a so-called legacy type mapping that handles class changes. Then we abstracted the file system so that you can store your objects wherever you want. Then we implemented the kind of like garbage collector that works on a file base, similar to the garbage collector of the JVM that works on a memory. Then we added database connectors that we are able to store the objects in relational databases as well as in NoSQL databases, also in-memory data grids, Kafka, and plain files. On top of that, we added a REST interface and a graphical user interface that you can use to browse through your storage data. And then we added some native backups so that you can decide if you want to use the native backup functions or the backup functions of your database system. And this complete package we have open sourced. So we support all major database systems. You can use MicroStream as a tiny persistence library. You can download it via Maven, use it with all JVM languages, even on Android, and it even works with GraalVM native images. So you can use it wherever Java runs. The only requirement is Java 8. And the benefits of this performance is now you can really build incredible fast applications and build revolutionary new innovations, features, and products. And with this performance, you're also able to save lots of CPU power. In customer projects, sometimes we save up to 90% costs of infrastructure because the workload of a traditional cluster can be handled by only one single JVM with MicroStream. And actually, it's not managed by MicroStream, it's managed by the JVM. MicroStream is only responsible for storing and loading the objects behind the scenes. And for developers, it's really comfortable to work with because it's fully object oriented. You don't have to care for any database specific data structure, no more data conversion behind the scenes, no more annotations, no super classes to implement or interfaces to implement. So just POJOs. And this is really simple and convenient. And MicroStream is not a prototype. It's production proven since more than 10 years. And the company is founded in 2019, but the project actually was started in 2013 already. And so this is absolutely stable. And this is also the reason why we now integrate MicroStream with project Helidon. And this is why we think that MicroStream is really a great fit for microservices because it's a tiny persistence that is kind of like micro persistence. So fits perfect for microservices. And at this point, I like to introduce and welcome Dmitry Kornilov. He is the project lead of Project Helidon. And welcome, Dmitry. Hello.
Hello. Thank you, Marcus.
Great to have you.
Thanks.
Maybe you can tell us something about what actually is Helidon and what's coming up with the next version of Helidon.
Sure, we'll be happy to. So for those who doesn't know what Helidon is, it's a microservices framework developed in Oracle for creating cloud native Java applications. It's open source. You can find it on GitHub. It's licensed under Apache 2 license, so you can fork it if you want. It's used by really many internal teams and external customers, and they like it. Why we like it? Because Helidon is really small and super fast. Because we support modern standards, Java standards like microprofile and partially Jakarta EE. Because if you want to go insane fast, it's possible to use Helidon reactive APIs and compile your application to native executable using GraalVM native image. We have an early support for Project Loom, and actually there was a talk by Thomas Lankert earlier today on JCON. If you missed that, you can watch the recording, and there are a few more sessions on JCON about Helidon. So if you want to learn more, please visit it. And today I'm here basically to announce that we are integrating with MicroStream, and this is upcoming integration. This PR has been merged already. And it will become publicly available in our next version, which is 2.4.0, which is going to be released later in October. I do believe that MicroStream with Helidon is a really nice, kind of powerful combination because we have a fast microservices framework, and MicroStream really feeds into that concept. That new release of Helidon, which is coming later on in October, will also include some other features, like, for instance, microprofile array support, arrays, long-range actions, additional Java 17 support, Oracle ATP support, and huge number of performance improvements, bug fixes, and other enhancements. Thank you.
Thank you, Dimitri. Fantastic. So we are really proud to be contributed to Project Helidon and working together with you guys. And beyond persistent, there is one more thing that might be interesting for you guys, and is all about serialization. And at many Java conferences, we talk about the issues of Java serialization, and that is a huge security issue in Java. And Mark Reynolds, he said that 50% of all vulnerabilities in Java are linked to Java serialization. And it was a horrible mistake. And why? It's because with Java serialization, it's possible to inject malicious code and to execute malicious code through deserialization. And this is a huge security risk. And there are various speakers at the Oracle Code Conference who show how scary easy it is to inject code into a Java server that is connected to the internet. And with MicroStream, we do it completely differently. So this was not the core feature actually of MicroStream, but yeah, we did it completely differently. And this is the reason why it is not possible to inject and execute malicious code through deserialization. So if you are looking for high secure serialization for your business applications, then you should check out MicroStream and try it out if MicroStream can help you to solve your issues. And as I mentioned, it also works with GraalVM native images. I'd like to announce that we start MicroStream Summit in November on 4th. And it's a one-day online conference. I'd like to invite you all together to join our conference. It's free. You can enroll for free. And the next session is about developing in-memory systems with MicroStream. We explain how MicroStream works, how the approach works, and explain the concept, how the storage works, and browse through some code and show you some code. And then you also can ask question. We will have a small Q&A with our CTO, Florian. Thank you, everybody, for joining, and thank you for watching, and have a great day at JCON. Have a great week at JCON. Thank you. Bye-bye.